Hi, my name is Michał Adamkiewicz and I'm the co-lead of the Stanford University Mars Rover team. This is our first and what we hope will be many entries into the University Rover Challenge.
Our team is divided into 4 different sub-teams: mechanical engineering, electrical engineering, computer science, and scientific analysis.
I'm Christina Lee, and I'm the mechanical lead for the Mars Rover project. The rover was designed out of mainly sheet pieces so we can make laser-cut Duran prototypes early on, then water-jet cut aluminum sheet metal that we're TIG welding together for the final product. Throughout the design cycle, FEA analysis and optimization software were used on all parts to minimize weight while ensuring that all components have a safety factor of 3 or above. Our 4-wheeled rocker suspension allows us to achieve higher torque outputs, lower weight, and greater mechanical simplicity. We're using powerful DC brushless hub motors, allowing us to drive up 45-degree slopes. We use custom-designed 3D printed wheels, purposely picking the 3D filament to be grippy and flexible. They slightly conform to the ground surface, giving us more grip on hard rocky surfaces and more surface area on soft sandy surfaces. Our double-layered chassis has a designated space for every electronic component and removable panel so we can swap out components easily. Additionally, the top can be easily detached for more extensive system repair. Our 5-degree of freedom arm uses a counterbalance system to decrease the load on our belt and pulley transmission systems. The arm is entirely detachable, so we can remove it for the autonomous traversal task and reduce weight. Our gripper is reconfigurable to 2, 3, and 6-finger operation so we can adapt it for the different tasks. 2 fingers to grip handles and 3 fingers to use tools like a screwdriver concentrically. For the science cache task, we have an auger to collect the soil sample and release into containers on the chassis for onboard analysis. The simplicity of the system keeps this end effector lightweight.
My name is Shai Tuck, and I'm the electronics lead for the Stanford Rover team. In addition to the sensor board being used for scientific analysis, we're also working on our power distribution board, which will eliminate messy wiring and improve reliability. The design features a latching and fail-safe e-stop, as well as fuses to shut off power on overcurrent events. We are working with another student group to develop a long-range radio which will allow for us to maintain low bandwidth communications even out of line of sight. We understand the difficulties of running electronics in the desert. This is why we are doing extensive thermal simulations of the boards, ensuring our enclosures are properly cooled and sealed from dust, in addition to conformal coating all of our boards. All of our connectors are keyed and have positive retention mechanisms.
Hi, I'm Victoria.
And I'm Rachel, and we're the CS co-leads for the team.
Our main onboard computer is the Jetson TX2, which runs the robot operating system and controls all rover subsystems.
For the autonomous task, we will be using visual odometry from a stereo vision camera system combined with GPS using a Kalman filter to position ourselves on a map. In addition to being able to track tennis balls using traditional methods, we are using deep learning for image segmentation to identify and localize obstacles like loose sand that wouldn't be detected by a traditional system but are still difficult for the rover to traverse. To run these models, we are using custom open-source ROS packages I built while working at NVIDIA.
We are currently working on inverse kinematics, but we're already practicing for competition tasks using direct control of each joint. For precise and intuitive operation, we are also experimenting with the master-slave system for arm control.
We use a commercial off-the-shelf 2.4 GHz antenna system for maximum reliability and throughput.
I'm Nick Lai, and I'm the science lead for the Mars Rover team. We will be doing preliminary analysis using the onboard cameras to look for signs of water in the Martian landscape. We will be taking measurements of conductivity, humidity, and temperature using solid-state electronics. Finally, we'll be using fluorescent dyes to distinguish between nucleic acids and other molecules. This has the advantage of being a more selective and sensitive method that we can do in the allocated time.
With our robot nearing completion, from here on out we plan to focus on increasing reliability, preparing procedure checklists, and systematically testing everything.
We are proud of how far we've come this year and are excited to compete in the University Rover Challenge.